Cool. Okay, so hopefully everybody can see this. I'm sharing.
Yes.
So a little bit about me. This is my social media, my blog, my hub, and my squad. We're called Red Naga. And if you ever want to join and talk about Android reversing, or you have some questions, or you want to contribute to any of the projects I'm going to talk about, there's our Slack right there. And my job title is Head of Innovation at SentinelOne. Before that, I worked at Lookout Mobile Security, where I got a lot of Android malware experience. I built a lot of tools around Android. I built like if you use Smalley, which is the language of disassembled Android apps. If you have Smalley on GitHub, like I wrote the syntax highlighting for that. Uh, yeah, so I've been doing this for a while, but it's not really my day job anymore. It's a side project. So yeah, what is obfuscation? Real quick overview. What is it? Why care? I don't want to just start talking about how to deobfuscate. I want people who are unfamiliar with deobfuscation to have some idea who cares about it, why they think it's interesting, why it's a valuable problem, why it's worth learning and thinking about. And I assume that there's 20-something people here. Not everybody's going to be an Android reverse engineer, so I'll do a very quick Android overview. You can learn some vocabulary. You can learn some of the words that I'm going to be using, and somebody interrupt me if they have no idea what I'm talking about. And then I want to give some examples of obfuscation. It's one thing to talk about, how to deobfuscate. The best way to really learn this is to try to grapple with it and try to solve it yourself. So I'm gonna go through some examples and try to ask you to think about how you would solve it. And then I'm going to talk about 3 tools uh, that are used for identifying obfuscation, and two different tools that take completely different methods for doing deobfuscation. So there's Oracle, which uses patterns, which is basically regex, and an Android emulator. And there's Simplify, which uh, uses its own virtual machine to kind of execute all the code and understand what it does, and then deobfuscate from there. So what is obfuscation? Really simply, it's intentionally making the code difficult to understand. So it's a very general term. You can use the word obfuscate to mean making something difficult to see or find. There are legitimate and malicious use cases for obfuscation, of course. So you might want to use it to hide intellectual property. If you have some really cool algorithm and you don't want people to steal it, or if you have a video game and you don't want people to understand how to write cheats for the game, or you just want to make it difficult for analysts to figure out what's going on, you can obfuscate your code. And also malware uses obfuscation. They typically pull some tool or off the shelf and run their code through it. So very, very little malware is not obfuscated. So if you're doing malware analysis for Android, for example, you're going to need to have some familiarity with the obfuscation. So I always think of this of code golf. It's a game. I'm not sure if you guys have heard of it, but the purpose of golf is to have as low a score as possible. So code golf is trying to write a program in as few numbers of characters as possible. And this is a program which solves FizzBuzz, which is an interview question. So you count from you count up your numbers, and it's supposed to be every time you have a number that's divisible by 3, you print fizz. If the number is divisible by 5, you print buzz. If it's divisible by 3 and 5, you print fizzbuzz. And it's a very simple algorithm, and it's meant to be easy enough that like an entry level computer science, software engineer interview question, it would be easy to do. But in code golf, you want to write it in as few numbers of characters as possible, and it's not intentionally obfuscating the code, but one of the byproducts is that code is more or less unreadable. And if you were on my team and you committed code like this to the repo, I would -2 it in the code review, and I would say don't ever write code like this in production. But the way you would say this is Python 3. This is a solution to FizzBuzz in 56 characters. And you can I think whenever I think about obfuscation, I always think about code golf. It's not totally related to the talk, but it's fun to check out if you ever want to learn the real ins and outs of a language. It's actually useful for understanding how obfuscation works because you have to flex your brain in weird ways to try to understand how you can make the code smaller. So yeah, not really useful. So why you'd want to care about deobfuscation, I talked about it a little bit, but companies with malware infections, they need to understand what malware does. So they're going to have big questions like, oh man, we got infected. It hit 20 machines before we stopped it spreading. How bad is it? What was the malware doing? Is this APT from China? Did they just steal all of our IP, or was this just a Bitcoin miner, crypto miner that didn't exfiltrate any information? Let's give it to some analysts to figure out what it did, and then the analysts are going to have to deal with obfuscated code. We have to figure out some way to tear it apart. Or if you're a security researcher and you're investigating an application to try to understand, if there's privacy issues or if there's, something interesting with it, there are security researchers that, for example, look at every single Microsoft Windows patch or just patches in general to try to understand what's going on there. So in this case, if you're looking at Zoom, you might wonder why it's using broken encryption and occasionally sending data to China. And this was a real question that came up. I'm not sure if Zoom is obfuscated, but this is sort of question you'd want to ask and answer. And then if you're a pen tester, you're trying to find vulnerabilities in code. You're trying to find bugs. You're trying to find exploits. You're going to want to, you might come across apps that are obfuscated, and you're going to need some sort of tools and familiarity with the obfuscation. And also, for the record, bad people also care about the obfuscation. And you can kind of tell when one of these people, they just want to pirate software, they come onto GitHub and they open an issue and they say, hey, help me deobfuscate this commercial application. And I usually tell them that I prioritize malware and to go away. But yeah, there's quite a few people like that. Real quick, Android overview. I want to get some vocabulary out of the way so that I can use jargon without holding anybody's hand. If you're totally new to Android apps are zip files with a .apk extension. So there's nothing special there. The APKs are filled with all sorts of resources, libraries like native code, C code, C++ compiled to native libraries, and also Dalvik executables with the .dex extension. Android apps are created with any sort of JVM, Java Virtual Machine language. So that includes stuff like Java or Kotlin. And I assume you could probably also make Android apps with Scala or something like that. DEX files run on something called the Dalvik Virtual Machine, which is very similar to JVM. It's so similar that, Google and Oracle went to court over it because Oracle said Google stole some stuff from them to make Dalvik. So they're very, very similar. There's a lot going on with Android apps, but since we're just focusing on the code, I'm skipping over a lot of details here. Another important thing that if you come from Windows or Mac or Linux, you're used to decompiling native executables assembly language, is that DEX files are different in that they're very easily disassembled and modified and then reassembled. It's almost trivially easy to do for almost every DEX file. They're malleable. And they can also be executed from the command line. You could actually take a DEX like you would take an executable in Windows and just run it inside of an emulator. You can make your own little programs from the command line, and it's a good learning tool. But it's important for how Oracle works, which is why I mentioned it here. So I'm going to get into the different types of obfuscation. The first one is identifier remapping. Then I'll give examples of each of these. Remapping identifiers, literal encryption, white noise, reflection. So if you're used to Java, it's that type of reflection. And then there's others that are outside of the scope of an hour. They would take, like species to talk about, and that's sort of virtual machine obfuscation, which is really cool. You basically implement a virtual machine inside of a program, And whenever you want to do something, you download a sort of script of that virtual machine and execute it within the VM. It's very, very difficult to deobfuscate those types of programs, but that type of obfuscation is also very complicated, so it's very rare. Well, it's pretty rare in Android. And then there's also control flow obfuscation, and of course packing. Packing is probably the biggest type of obfuscation, but it's covered completely differently than how you deobfuscate code. Basically, you take a DEX file and you hide it inside of an APK, and you unpack it at runtime. You sort of decrypt it and load it at runtime. So if you're just looking at the APK, it doesn't look like it's there. It doesn't look like it has those DEX files. And but it's solved completely differently. So I won't be talking about unpacking here. So identifier remapping. This is an example of a decomiled application. And these are some of the classes and methods and variables in the application. And they've all been renamed to be very annoying to understand. So you'll see the same name repeated over and over again. There's lots of I's and ones and L's and zeros and O's and capital O's. And these identifiers are things like class names, method names, variable names, and they've all been remapped to something more difficult to read. When you strip this information out, it's much more difficult to understand what's going on. There's a method here which might have been called decrypt string, or a method here called, annoy user or do something evil, and you're not getting any of that information anymore. There's no reason to deobfuscate that because information is basically lost. It's sort of like if you have a photograph and you scale it down, you turn it into really low quality JPEG. Well, that information's lost, and there's no really easy way to get it back. Then you have something like literal encryption, where a literal is anything like a number or a string. It's typically you're going to see string encryption. That's probably the most common. And this is a very super simple example of what you might see. This is Python, so this isn't even disassembled yet. I'll show you a real example in a second. But if you're looking at this code, you see n equals base64 decode what appears to be a base64 string, and then send premium text message to n. So looking at this, all you know is that n is probably a phone number. So by the way, if you're not familiar with Android malware, a very common monetization technique, maybe several years ago, was to send premium text messages, which cost the user money. That's why I use that in the example here. So if you're looking at this and you're just deadlisting it, you're just looking at the code, you're not actually running it, you're not running any scripts or anything, and you want to try to understand what it's doing, you can kind of understand this, but it would probably be nice if you knew what number it was being sent to. You got to ask yourself, if you were given this code and your task was to come up with a way to make it easier to read, maybe decode that string, how would you defeat this? I mean, you want to take a couple seconds and really think, what would you do? If someone wants to say something, that'd be great.
You could just go to base64 decode website and copy that string and decode it, I guess.
Yes. That's like the base level is manually deobfuscating all the strings. So you could, because this is such an easy example, it's base64 decode. If this function was called, ASDF and didn't have a useful name, then you'd have to look at that function, you have to reverse engineer that function, try to figure out what it's doing, and maybe implement that function yourself, and then take that string and call it in your script. Or if you were trying to automate it, maybe you could take, your script could look for base64 decode, and then pull out the string that's going to be decoded, base64 decode it, and then replace that function call with the decoded string. That's one way of doing it. Sort of like making a script specifically for deobfuscating this. And a lot of people usually stop at that level. A lot of people, if they do any deobfuscation at all, they might make a one-off script which works for a particular piece of malware, for a particular type of obfuscation. very specific. This is a real example from some malware called OBAD, and there's a lot going on here. And there's not going to be a quiz at the end, so you don't have to memorize everything that's happening here. I'll just sort of walk you through it really quickly. You have what appears to be a base64 string, and that's being passed this unreadable function here, and it gives back a byte array. And that's stored in v2. So v2 has a byte array. Then you have all of these numbers here, so being stored in the v3, 4, and 5. That gets passed to this function. That gives you back a string. So now you have a byte array in v2 and a string in v3. And for v3, you get the bytes of that string, and then you call another function with those bytes, and you get a string back. Then you give it the original bytes you got and the sort of transformed string bytes. You get another byte array, and then you turn that byte array into another byte array, and then you turn that byte array into the decrypted string. There's this isn't something you could just look at and go to, a website and decode it. If you think like, how would you defeat this? How would you get over this type of obfuscation? So yeah, it's a bit overwhelming. Like you might think, okay, you could write a script for it that works. Maybe you reverse engineer all of these functions and you write your own implementation of it in Python. And you have a Python script that goes through and looks for this sort of pattern and then this sort of pattern and calls the functions with these inputs. So in this case, it looks for this static and move result object, pulls out this string, calls your implementation of this and gets back a byte array. And you would do that for every chunk. And that's definitely one way to do it. It's a lot of work because you have to reverse engineer each one of these functions, and that can take days. So that's where Oracle comes in. So the way Oracle works is it has a bunch of plugins. The plugins are fed that app code, basically the code I just sent you. It would be given that, and then it looks for patterns, and then it pulls out bits of code using those patterns and builds a small driver program. It's a little DEX file that will use reflection, basically Java reflection, to execute those real functions using real arguments on an emulator. And then once it knows the output of those functions, the real output, you didn't have to reverse engineer anything. It just calls the code that was there with the inputs that it was going to be given anyway and gets the output, and then it can replace the obfuscated code with the emulator output. I'll walk you through a quick example there. So here's part of the code that we just looked at a second ago. It takes the 3 numbers and gets back a string. And here's what Oracle would do. There's a plugin specifically for this type of malware that has a bunch of complicated regex, which again you don't have to understand. You don't have to pick your way through this. This is going to look for those 3 constants, and then the invoke static, and then a method that takes 3 integers and that returns a string, and so on. It will pull out those arguments. It'll say, okay, I know these 3 numbers are what you want. This is the method that I'm going to execute, and this is the register where I'm going to put the result, v3. And then it creates a driver dex, and the applications dex file, so the actual applications code, and it puts them together using a program called dexmerge, which is part of the Android SDK. You don't have to use dexmerge. There's a lot of other ways to do this. The idea is pretty simple. You're just going to put that real code from the malware onto an emulator, and the driver is going to execute all of those functions that it's seen using these real arguments. The idea is it will be like you were running the code, and you'll be able to peer into what was going to happen when you ran it and get some idea of how it was going to behave. So let's say the output was a string saying, journey before destination, which is a quote from a good book. Then it would take that string and it would replace all of this complicated code and this call to this decryption method with just a single constant with that one string. And the idea is you have lots of little building blocks, lots of little plugins that are looking for these patterns that you've seen before, that you can sort of make a giant bucket of plugins, and it will run this sort of pattern search and then emulation over and over again until nothing is found. So maybe the entire program isn't deobfuscated just from this, but maybe because you have a string there now, a const string, whatever code comes after that is now easy to deobfuscate, because now you see the input is going to be a string and you know what the input is going to be by looking at the code itself.
Caleb, can
Yes.
I ask any questions in between or at the? Okay. So I
Yeah.
have a question regarding this particular piece of code that you mentioned. So in the app, this might be just one, maybe 10, 15 lines of code in the entire application. So does Oracle identify such snippets of code on its own, or do we need to supply that to Oracle and then it will work its magic?
Um, you do have to tell Oracle basically the patterns to look for. And there are a few generic patterns you could look for, like it takes a byte array and returns a string, and it's static. And you can sort of assume that certain methods, certain patterns you can always call. Um, Basically, the way Oracle works in practice is that whenever a new type of obfuscation is released, like DexGuard, whenever a new version of DexGuard comes out, or whenever some new obfuscator version comes out, you have to update the plugin or create a new plugin to look for those patterns.
Okay, and also you mentioned the driver decks and the app decks. So, and that, once you have the plugin and everything, then it will show it on the simulator or on the phone. So, but there might be some dependencies before the code, which might also be required. So would that be also taken into account, or would that be needed to be added manually?
Right. Yeah. So if there are dependencies, you that we're getting into some slides that I'll have a bit later, which is the
Yes, sure.
cons. Yeah, like why Oracle isn't good. But that's a good question. Um, you're kind of limited to static methods because static methods don't rely on any instance members, so they don't rely on as much state as like an instance method would. It's a static method is most of the time a static method's state that it cares about. It's just the arguments that you give it. It kind of does the same thing all the time. So you do have to do a bit of analysis to say, like, does this static method reach over the network to do something? There are a lot of ways to defeat Oracle. So you could say, I'm going to reach out to the network to do something, and that probably wouldn't happen if you just tried executing a dex file on the phone because you don't have permissions. Or it could look at the stack trace to see, am I being executed from within myself, or is someone using reflection to execute me? And if they're using reflection, then do the correct thing. So yes, there are dependency issues, and it's not usually as much of a problem for many types of obfuscation, but it is a problem for certain types of obfuscation. So Oracle is kind of limited in that regard.
Thanks, Caleb.
Sure, no problem. So yeah, the pros is that it's very simple. It's written in Ruby. I could probably rewrite it in Python in a couple of days. I wrote it in Ruby back when Ruby was cool, so 3 years ago. Uh, and all it does is run a bunch of regex on code, find those patterns. The hard part is in the patterns. Creating those patterns is very difficult. Creating those regexes and understanding the obfuscation is difficult. Writing those plugins is the hard part. But Oracle itself is fairly simple. The idea is you take some code, shove it into a dex file, put that dex file on an emulator, and run it. Another thing you could do, another trick that's kind of like Oracle, which is actually what led me to make Oracle, is you can use dex to jar or injarify, which are full, like they can completely decompile something back to Java code again. So if you give it an Android app, you give it a classes.dex, you give it a dex file, it will turn that back into Java source code. that's not very good. The source code isn't very readable because there's a lot of information that's lost, and decompilation is an ugly process. But what we were doing at Lookout to do deobfuscation at first was we found out we could just take those jar files and then import those jar files into a Java project. And then inside of Java, we would write a little driver program that would call the decryption routines. Maybe we'd set up whatever state we needed to, create instance variables, do whatever we needed to, and then we'd decrypt very specific parts of the code because it's hard to automate. And Oracle is just a streamlining of that. It's the sort of automating of all of that. And when it works really well. Problem is it doesn't always work. And it's also very fast. Some of the cons are it's really hard to automate anything other than static methods. Static methods work best. The stack trace is wrong, so it's possible for someone to know they're being deobfuscated. It doesn't generalize well, meaning you have to update it for every new type of obfuscation you see. But instead of writing a new script for every type of obfuscation, you write a small plugin that does a good chunk of the deobfuscation for you pretty quickly. And you have to be familiar with regex. I consider that a con. The best regex is no regex. And not all obfuscation is easy to do with patterns, which I'm going to get to right now. So here's an example of a type of obfuscation called white noise. In this case, this is arithmetic white noise. So you have this very simple function here. It takes A and B. I believe you can probably hear some sirens. I'm sorry about that. The code's very simple. X equals A plus B. Something happens with A, something happens with B, something happens with A again, but then you just return X. So looking at this code, you can say, well, unless I'm being tricked here, this is like some sort of like mind game, then those 3 lines there are not needed. They don't do anything. They don't affect state outside of this method, and they don't affect the state of the return variable. So they're basically dead code and they can be removed. And this isn't something Oracle can do very easily. It's not, Oracle really can't tell you, if there are side effects to a method. The question is, how would you defeat something like this? How do you know if code is dead and can be removed? Because ideally, you just rewrite this function in one line, x equals a plus b, return x, or return a plus b. Think about this for a second. How would you analyze source code and know if a variable is used? You could say, well, if you could go through line by line and see if a register or a variable is used somewhere in the chain before it's returned. You might be able to kludge something together like that. Yes.
Maybe just check the memory where X is stored and see if it is being modified.
What was you broke up for just a second there? What did you say?
Maybe we can just check that memory where X is stored. Okay.
Memory access?
Yeah, memory. I mean, like if it is a C, we say that what's the pointer to X, where X is value of X is stored. Okay, and we can see if that value is not changed. Okay, we can look at.
Yeah, that actually might work for native applications if you were running them, and you had that sort of access. In this case, it's a Java-based language, and all you have is the source code. All you have is dead listing.
Yeah. And then second is like if you basically write a simple file parser in Python and say, okay, what is returning X, then we just backtrack and see what are all the lines where X is used, and if there is a line where X is not used, just delete that line.
Yes, yeah, like that gets you pretty close. The problem is, okay, so that I think I did something like that at first. And then the problem I ran into is that sometimes there would be, let's say instead of a plus equals 5, it'll be a equals some function call. And then you need to go into that function call and see if that function call affected state somewhere. Maybe that function call did something important and you can't delete it. It needs to stay there, or the semantics of the method change. So it might write something over the network, or it might delete a file on the file system. Your first guess is pretty good. That's where you'd start for sure. So then, I will resolve that question very quickly. But one more example here, and that's reflection. So if you're not familiar with Java, Java lets you use it has this technique called reflection, where basically you can refer to things by a string. So in this case, you're getting a class object, and that is coming from a string that has been encoded. So you're looking at this, and if there weren't comments telling you what class it was getting, you'd have no idea what class it was loading here. And then it gets a method from that class. In this case, you can see in the comments, it's going to be getting the method send text message, and then it's going to invoke that method. So if I take those comments out, this code becomes indecipherable unless you can somehow decode those strings. And Oracle kind of works for this, but it's pretty hard to. It's brittle in that if any one of these things changes in the disassembly, the patterns are very brittle and they break easily. There's a lot of different ways to do reflection. There might be a check cast somewhere in there to cast the results of something, and it gets a little messy to do with just patterns. You actually need something that really understands what's going on. This I have no idea how you'd even start attacking this. Go to simplify. So simplify, the sort of formal way of saying what it does is that derives semantics from virtual execution in something called small EVM. And semantics is just sort of the behavior if you understand what the program does. If a jump predicate is unknown, both branches are taken. If you get to an if then, and you don't know the value of the variable inside of the if, then small EVM is capable of dealing with that. It says, no problem, I'll take both execution branches and we'll see what happens. So if you're executing a method that takes some arguments, you don't always know what those arguments are going to be at runtime, especially if it's a top level method. You're just trying to decode it. You're not always sure how it's going to be executed. You want to try to figure out as much as possible when you execute it. So it takes all execution branches. This will make a little bit more sense. I have some graphs later to show you. That means all possible states are recorded at every op for every execution path. The sort of memory requirements for this get very, very high because you're recording everything that could happen in an application, and the number of things that could happen grow considerably the more things that are unknown. Then once you have this sort of semantics, you have this sort of graph showing you every possible state that an op could be in. There's certain simple optimization strategies that are applied repeatedly until there are no more changes. So I'll go through some of this as an example so you can see what I mean. So here's some small code here where you have a constant 3 is being stored in v0, 5 is stored in v1. Then those v0 and v1 are added together, and v0 is returned. So this should return 8 when you call it. And what small EVM will do is it'll start at const v0, ox3, and it'll set v0 to 3. It's actually a lot like an emulator, but it's capable of dealing with unknown values. If you gave this to if you gave unknown values to an emulator, it would choke itself. It would freak out immediately. Then it goes on to the next opcode. It sets v1 to 5, so now it knows what v0 and v1 are. Adds them together. Now v0 is 8, and then it returns 8. Very simple example. The interesting stuff happens when you get to some code that has a jump, an if. It's a little bit more complicated. It takes an integer, and it returns an integer. It sets v0 to 1, And then if the first argument and v0 are both the same, it will go to end. Otherwise, it will add v0 to itself, which would be 2. So it's either going to return 1 or it's going to return 2, depending on what p0 is. So if p0 is equal to 1, execution is super simple. Goes through, sets the state at each one of these nodes. Node is the jargon I use inside of Simplify or small EVM for an opcode. Then returns v0, and v0 is 1, no problem. Interesting stuff happens when you don't know what p0 is. So if you're executing this method in small EVM, and you don't know what the arguments are going to be, that's fine. Just a second. Okay, so the graph looks a bit more complicated. You start with p0 is unknown, question mark. And it says if p0 and v0 are equal, go to end. Well, geez, I have no idea what to do. So I'm going to assume either one could be true, and you get to what I call the multiverse. So there's no consensus at the very end for what v0 will be. v0 could be 1, or v0 could be 2. So if you're trying to optimize this method and you're trying to say, what does this method return? If you don't give it any arguments, you don't know what it's going to return. This becomes important later on when you're trying to do certain optimizations that I think will make sense here in a second. So the next couple of slides are the slides that have all the code in it. I tried, you got to have a little bit in there because this is a pretty technical topic, and I think these actually explain it the best. I could just talk about it, but I really wanted to show you code, so bear with me. I'll walk you through it so it's not too difficult. You get a byte array, then you base64 that, decode that byte array, and you get a string and print it out. That's what this main method is going to do. The way you would execute that using small EVM is very simple. It's Java, so you have to have a factory. That's like required. So you have a virtual machine factory. Then you create your virtual machine, and you say, here's where my small e code is. In this case, it's a small e path. This could be a directory or folder on your computer. And then in the simplest case, you just execute it. You'd say, execute this method signature, and you give it the full method signature. So this is how you would write basically this main args as string array in returns void in small e. This isn't very useful because you're not really getting the return value. You're not really getting a graph. But this does show you, it's very, very simple if you just want to execute something. A bit more interesting is if you wanted to have it print something out. So if you look back at this code, there is a system.out.println. But if you ran this code, you'd notice you wouldn't actually see anything printed out. And that's because of an important concept. And that is, anytime there's any state change outside of the method or the class or basically outside of the application, any sort of state change is going to be prohibited. The idea is you don't want any malicious code to take advantage of small EVM and to write to your file system or to open a network connection or to do anything. So the small EVM is very paranoid about doing any type of I/O. So system.out.println is not going to be executed or emulated in any way. But if you wanted to hook that method with your own implementation, it's very easy to do. And this comes in really handy if you want to define your own, like maybe you've reverse engineered some decryption that simplified doesn't work with. You could very easily replace those encryption calls with your own implementation. The way you would do that is you have a class that extends method state method and implements unknown values method. And there's tests for all of these if you want to understand what they do exactly. The constructor just sets the side effect level. It says don't remove this method call because it has a strong side effect. It might look like it's not doing anything because it doesn't change any variables anywhere. It doesn't change any class state anywhere, and you might think it's dead, but it's not dead because it's writing and doing some I/O. And this is the actual implementation. It's very simple. The execute method is given a copy of the virtual machine, the op that it's a part of, and the state of the method. And this is going to have basically all of the different registers, all of the different parameters, and what their state is at that time. Then I peek at the parameter for what is going to be printed out. I cast that to a string, and then I basically print it out myself. Then you would hook it by going to method emulator.add method, giving it the method descriptor of println, and saying, whenever you call println, I want you to call my version of println. So the normal version of println is not going to do anything because it has side effects. This way you could actually print something out. So now when you execute it, it will show the output. And this last bit here is this is probably the most important slide if you ever want to use small EVM, if you really want to understand how to get something out of it. This function here is called parameter logic, doing some sort of logic with the parameter you give it. It sets x to 5. If the parameter you give it is 10, it sets x to 10. And then it prints something out and returns x. It's sort of pointless, but it gives you enough meat there to something to play with. In this case, you would define the method signature. I'm cleaning it up a little bit so you can see how that looks. If you want to set method state yourself, you would go about spawning a root context. There's a lot of jargon here. I apologize. If you look at the test for a while, a lot of this makes sense. It's a root context because you want, if you imagine a graph of all of the different nodes and how they connect to each other, this node goes to that node. This opcode might jump to this opcode, or this opcode always goes to the next opcode. Then the very root of that graph, you're going to want the sort of beginning context of it. Context just means all of the state for this method. That this could be class variables change, or it could be method variables change. And you get the method state within that context, this line here, and you assign the parameter a certain value, and you give it a type. So if you're familiar with Android, you'll know that the parameter registers start after this register. So this is just a bit of housekeeping so that you're setting the correct parameter register, so they don't really start at 0. Then you execute that method, and you get back a graph. This is the first example where I really show you, or really play with the result value of executing something. And this graph is super cool because this graph, if you inspect it, contains every possible value at every possible op and every execution path it could take. For a lot of methods, there's going to be all sorts of state that's going to be important that's not going to be known. So a lot of the Android lifecycle things, they're going to be given an Android context, or they're going to be given a view, and those things aren't going to be available. And Simplify isn't going to be able to really understand what those methods are doing. But for a lot of obfuscation purposes, the methods that are important are methods that take a byte array, or they take like a byte array representing the encrypted bytes of a string, or the method that takes an encrypted string, or it's a method that takes like a decryptor object and also some arguments and eventually gives you back a string, or something like that. It's mostly a lot of string obfuscation that you're going to see. And in those cases, the important state that small EVM needs to understand semantics is all going to be fairly local to the method and the classes. And in those cases, small EVM will be able to properly execute that and understand what's going on. But if you're thinking in your head, like, there's so many limitations to this, there's so many ways this can go wrong, there's so many different ways the execution paths can explode into forever, you're right. And those problems are sort of mitigated using a lot of different strategies, which I'll talk about in just a second. But this works fairly well for the obfuscation, this sort of approach. You take this graph, and all of the optimizations happen on this graph by looking at it. So for example, you can do graph.get terminating register consensus of the return register. So terminating means for all of the opcodes that are returning or throwing, they're basically the end, all the opcodes in the method that are the end of the method, what was the consensus of the value of the register for the return register? If all of the multiverses agree that the return register had one value, the same value, then this item, this terminating register consensus will be known. Otherwise, it will be unknown. So if you're just executing a method that takes a bunch of arguments and you don't know any of the arguments, you're probably not going to get a known value at the end. There's a reason that method had arguments. You probably needed them. But a lot of times you'll execute a method that executes some other method. The top level method will build up some state, like encrypted bytes. It'll load up some encrypted bytes. It will fill an array with something encrypted, and then it will call this sort of decryption method. Now, when simplify does that, it'll say, oh, I know those encrypted bytes because I watched this method execute properly, and then I saw you call this function call, and I know what you called that. So you will actually have those parameters, those arguments, when you're calling those second and third level methods. So under the hood, we're done with most of the code, so that's good. There's still some technical bits, but you won't have to look at my Java code anymore. Under the hood, you can see on the left, this image is showing you all of the opcodes. Like I said, it's Java, so you have to have factories. I actually have tried to avoid having factories because I just thought it was too much of a Java joke, but it ended up being a really good design pattern. It made a lot of sense. It cleaned up the code a lot. So you can see implementations for all of the different opcodes you might be familiar with. And the way it works under the hood is APK index files are disassembled to Smalley using dexlib2. And dexlib2 is what the tool Smalley uses, and boxfolly, which are very common disassembly tools. Basically every Android tool like APK tool, everybody uses dexlib, or they use Smalley or boxfolly, which are made from dexlib. It's all from the same guy. It's like the oldest disassembler, really good. Those opcodes are mapped into this more simplified space. So there's 5 different if opcodes: if equal, if not equal, less than, greater, equal, greater than. Those all get turned into if, and the if opcode code handles them appropriately, and it ends up being like a couple of extra lines to implement all of them. Each of these ops, like array length op or compare op or fill array data op, they operate on method and class state, mostly method state. And maybe they'll set a register, to true, or they'll add 2 registers together. Usually the actual ops themselves are very simple. The hard part is keeping up with all of the state and having the virtual machine and being aware of all the silly things Java can do. You might wonder, if you ever download Simplify or Smalley VM, you might wonder why it's 100 megabytes zipped. That's because the entire Android operating system is included as Smalley. So whenever a function or whenever a method calls a system method or a system API, that API is available to Smalley VM. So you don't have to give it anything extra. You don't have to give it an emulator or an image or a framework. It will execute the certain whitelisted methods to ensure that only the safe methods are executed. So it's got the full operating system included with it. So with Simplify, the optimizations are theoretically very simple. Like if you have any kind of CS background, computer science background, there's not a lot going on there. The hard part is making sure that graph that gets returned is actually correct. If you can do that, then the optimizations are pretty easy. Some of these optimizations, if you're familiar with code analysis, are things like constant propagation, dead code removal. We kind of talked about dead code removal already. Unreflection, which is basically undoing Java reflection, and then various peephole optimizations. So that's, for example, like if you see a class is being reflected, you might want to replace that line with just the const class opcode. So that's they're little optimizations that don't really have a family, so they just all get lumped together in peephole. So I'm going to walk you through a quick optimization example, which I hope will tie together all the concepts that maybe I didn't explain properly or fully. I think this should sort of solidify everything. And if you have any questions about simplified, feel free to ask up after this slide. Let's say you start with some code like this. You have a big long string, and then you're calling with that string, you're going to call the decrypt function that's going to return a string. And then you're going to move the result of that decryption into v0. What simplify will do is if decrypt executes properly when you run this with small EVM, if decrypt executes correctly, and for a lot of decryption, there's not a lot of weird stuff going on there. It takes some string, it does some numbers, does some math, maybe some XORing, and boom, v1 should be known. And that means that move result can be constantized, can be replaced with a constant. This is sort of like constant propagation. We'll replace that with a constant, and now v0 has the result of the decryption string. Tell me of your homeworld, Usul. So the next step, the next way the optimization will work is we've already gotten the graph from decrypt. We've looked at the graph. We've looked at the terminating register consensus for v0. It was known. It had a constant string. We updated this code with a new constant. And now we're running optimization strategies again, and it sees that decrypt, the result of this call, is never used. So move result is never called after this method is executed. And importantly, because small EVM takes care to really pay attention to if there are side effects in the method, then it can tell you if there are no side effects or not. So maybe for some weird reason, every time you call decrypt, some counter somewhere in a class is incremented. Or maybe every time you call decrypt, it contacts a server to get a decryption key. In that case, decryption probably wouldn't have executed properly. But since it did execute and we did know the result, it still might have modified some state somewhere else, like in another class. Maybe it launched a thread, it did something weird. If there were no side effects, it didn't do anything weird, which is a very difficult question to answer, but if small EVM can answer it usually, it's dead and can be removed. So now you just have these two lines. And this first one, v0 is never used, so it's dead, and it can be removed. And you just end up with this last line. The small e code, simplify code, is littered with Dune quotes. I really like the Dune book, so if you're kind of like smirking because you recognize this line, then good on you. It's a very niche quote. So to wrap up simplify, the pros is it generalizes well with an exclamation mark, because generalizes well is an understatement. It's very hard to do. It's very hard to have a general solution, and there's like thousands and thousands of lines of code to do this. And another pro is that the functionality makes it useful as a library. So there's a little bonus at the end. I'll give you an example of how to use this as a library. Maybe you can make your own tools using small EVM or simplify. The cons, just to say, generalizing well is very difficult to do. That's why I put an exclamation mark there. But the cons are, it is like at least 100 times more complex than Oracle. It is so much more code. It's slow. It takes up a lot of memory. You run into things like the halting problem, which one day I was working on Simplify, after hours in the office, and I had my notebook out and I was taking all these notes and I was really excited. It's going to be so fun. And I was trying to figure out when do I know if a loop is ever going to exit or not? When do I know I've entered into an infinite loop? And I was trying to figure it out. And my friend walked by and he said, "Hey, what are you working on?" And I told him, and he goes, "Oh, good luck. Alan Turing thought it was impossible. It's called the halting problem, but good luck." And he just walked away, completely shattered my dreams. Um, the, the halting problem is impossible. So what simplified does is it puts a time limit on every method. If a method takes more than 5 minutes to execute, it assumes it's in an infinite loop and it bails. That's adjustable, it's configurable. Or it will only allow you to execute the same opcode 10,000 times before it assumes that it's in an infinite loop. Or maybe it only allows you to go a certain number of function calls deep. Like it only allows you to recurse a certain number of times before it assumes it's an infinite recursion. And also correctness is hard. And I haven't actually fully implemented, to my satisfaction, error handling. So a lot of people, not a lot of people, but some people have tried to make virtual machines like small EVM. And I always encourage them. It's great to see other people try this stuff, but they don't even try to deal with catch and throw because it is such a bizarre thing that'll happen. And I mean, don't even get me started on static class initializers. That's very weird. Like very few Java programmers can really tell you exactly when something is called in the class's static initializer. Is it when the program first starts? Is it when the class is first referenced? Is it when the method is first called? Like you have to know all these things if you're trying to recreate a virtual machine that does what Java does. So if you want to contribute, if I didn't scare you away with a bunch of technical jargon, and if you're still awake and I haven't put you to sleep, I encourage you to contribute, even if it's just to yell at me about a bug. But check the README. I put a lot of time into explaining how to hack on this in the README. Check the tests. There's actually like 80-something% test coverage. I could not have written this without tests. There's just too many details and too many regressions are possible. You can document a function. You can like adopt a highway. You adopt a function because I'm only one person and I don't have a lot of time to work on this anymore. You can also write some tests. Maybe you look at the test coverage and you see that some methods don't have very good coverage. You can write some tests. And you can also create issues. Like if you're analyzing any malware, Simplify doesn't work well, then create an issue and let me know. If it's malware, I'll generally find time to take a look at it. And also, if you've ever maintained an open source project, it is like Oz said, he said he was following my work for years. I had no idea. All I ever get is people complaining about bugs. I didn't think Simplify worked for years until a couple of people said I use it all the time. What are you talking about? I had no idea because people only complain. So like if you want to contribute, you don't have to actually do any code or do any hard work. You could just let me know, hey, I used it and it kind of worked. Thanks. And that will just keep me going. I'll be on cloud 9 all day. So a quick summary is that Oracle is like a shovel. It's sturdy, kind of. It's reliable. It does exactly what you expect it to do. It's very simple. Concept is very simple. It doesn't do everything. Like you can't build a house with just a shovel. It does one thing really well, and great. Simplify is like a fusion reactor. It's really complicated. People are pretty sure it should work. It's probably going to take a lot more time and money to get right, but when it works, it's magical. It's really cool. So I'm just going to go on to the next tool, which is ApkID. So we've talked about Oracle, we've talked about Simplify, two totally different ways of doing deobfuscation. ApkID is about. Go ahead, questions.
Sorry, Caleb. So I had a couple of questions for Simplify.
Yep.
So one thing was that does it add any extra code to the input file? Since like I was looking at the GitHub repository, and you give the input file and you give an output file, a location for the output file. So does it add any extra code on its own? to the output file?
Yes, it will take the input code and it will modify it to be simpler.
Right. But like, does it have any extra overhead of its own apart from the code? No.
No.
Okay.
Yeah, it's not going to add any new classes or any new methods. It's just going to try to rewrite existing code to be more simple.
Okay. And one other thing I wanted to ask, like you said, like if I just say the same words that you said right now, like when it works, it's magical. So could you share some specific malware samples that you found which you were able to work with using Simplify? That would encourage us to understand if, on a real life cases basis, which applications, which classes of malware, which future variants we could, benefit from by using Simplify.
So the README, that's a totally reasonable ask. The has two screenshots of a before and after Simplify, and I believe I also have the MD5 and the SHA-1 hash, maybe the SHA-256, and that is an actual sample you could download yourself, and you can play with that sample. It was the first sample where I absolutely needed something like Simplify, to de-obfuscate it. So it's part of the reason I built it. That sample would be a good start. Um, there are maybe you might be able to search Twitter for people using Simplify. I remember one guy mentioned it and had a sample hash there. That'd be a good place to start. And honestly, if you hit me up after this talk, I could probably give you one or two more hashes that are pretty useful. I haven't I haven't really done a lot of malware analysis in the past couple of years, so I don't have any modern samples that I've personally looked at, but I know other people have.
Okay, sure. I can reach out on Twitter.
Okay, cool.
Thanks.
Good questions. Yeah, I'm really like if we were doing this live, I would totally be able to look at your eyes and look see if you're falling asleep and see if someone like had a question. So doing this remotely is kind of a bit of a challenge, but I am in like my backyard, so that's great. Um, and yeah, just chime in if you have a question. Thanks. So we're getting to the end. We have ApkID. Uh, so identify different types of obfuscation. Um, Sometimes people really want to know before they're looking at something what type of obfuscation there is before they tear it apart and start looking. So this ApkID identifies compilers and packers, obfuscators, um, compilers, which is pretty cool. And you can do, and you can look for anti-analysis techniques. So if you take some Java code, you compile it using the Android Studio, that is a certain compiler. There's actually multiple compilers that you might use depending on how old your tools are. You might use DX, Jack, and you might use their latest one. I think I forgot what it's called. Yeah, there's like three or four maybe compilers or dex merge. Um, or you might have an application that has been modified with Smalley or box Smalley, and ApkID can actually identify that. I personally use ApkID for machine learning. So I'll use it on all of my samples. I have like 8 TB of samples, and I'll try to figure out what compilers they are. The idea is if I have a whole talk on this, giving you the really quick overview. If an Android application has been modified with box Smalley, it means probably someone other than the developer modified the code, and there aren't too many good reasons for that to happen, except for piracy and adding malware, and some weird people will like localize an application. Some automated tools will use box Smalley, but there's it's a very weird thing to see an application that's been like on the Google Play Store that's been modified with box Smalley, and ApkID can identify those things. It uses Yara rules, and it used to use its own custom DEX module, but ever since I PR'd my DEX module to the Yara repo, I think they were like mad or something. They were indignant, or they my code was so bad it offended them, and they wrote their own DEX module, which is really good, and it uses the Yara rules and the Yara's DEX module to do all this fingerprinting. It's very easy to contribute. There's a pretty good community. Unlike Simplify, which the code is honestly a little complicated, ApkID is a lot easier. So you can see there's 14 contributors. The last committer was pretty recently, and the last committer isn't me. That's always cool. And this is under the Red Naga repo. So a quick example of what the output looks like. I run it on a directory full of stuff called test data, and you could see this one evasion.apk has some anti-VM stuff where it checks the build model, checks the build product, network operator name. These are all ways you would check to see if you're in an emulator. Says the compiler is DX, possibly been DEX merged. It says the manipulator was DEX merged. It kind of gives you similar results for all of the files inside. So this one, it can actually tell you the packer. Sometimes, especially for unpacking, which we don't really cover in this talk, you want to know what the packer is so you can use the right unpacker. And sometimes identifying the packer can take a while. Maybe you write your own YAR rules or something. ApkID is just a nice centralized way of doing that. Every people who need to identify packers and compilers all sort of contribute their rules there. Okay, this is a little bonus. I told you I would give you an example of a tool that uses small EVM as a library, and it's called SDBG. And it's a GDB-like debugger for small EVM. So probably not a lot of people have used GDB. I mean, unless you've done a lot of reverse engineering or debugging. It's like that. It's the same sort of interface, but it's for small E code. You can step through the code and inspect the state. I basically did something similar with IntelliJ and setting up breakpoints inside of small EVM. Instead, I made the code much cleaner, and I created a debugger class that did this for you. So if I'm personally going to debug something in small EVM, something's wrong with it, I'll probably use SDBG. So it's useful for exploring little bits of code. It's a lot easier than setting up a full Dalvik VM debugger, and it's very small. It's written in Kotlin. It's only maybe 100 lines of code. 98% of the code is done by small EVM. So I have a little video that I hope you can see, and it's about a minute long. I'm going to play it, and just to give you an example of what SDBG looks like. So I'm going to run it with this small directory as input, and I'm going to give it a function called hello world. So it's going to load up all the smally, load up the framework, and start the debugger. This prompt, I can list all the code. I can see the line numbers. That caret at 0 says that I'm currently at 0. Some constants. I'm filling out an array, and I'm passing that array to decode, base64 decoding an array. Set a breakpoint at line 6. I look at all my locals. Everything's null. I take a step, and I can see that V2 has been populated with the value 16. So I can see that first opcode executed, and I can look at what was in that register. Then I continue to the next breakpoint, which is at 6, and I can see I have some arrays initialized, and I had some unknown values. So I can step, and I can see hello world. So it was very easy. This is just like debugging, but instead of debugging like a C program, you're debugging small EVM. And it's not a true debugger because you're not really truly emulating the code. You're doing this weird sort of, I don't care if I don't know what a value is. I'll just take both execution branches type of execution. And it also won't execute like different IO functions. But it's pretty good for debugging like actual obfuscation. I'm just skip to the end. Yeah. So references here in the slides. This is the link to Oracle. I call it Dex Oracle, Simplify, ApkID, and 2 tools that were really useful to me. They were very educational. One of them is Suit. It's a Java optimizer. I stole/borrowed some ideas from them for how I made Simplify. I didn't use any of their code, but they had some really good concepts and some really good papers. And Unicorn, which is a CPU emulator. I worked at the same company that the guy who made Unicorn worked at. I met him a couple of times. That project it's very cool. I think it's a little bit more applicable than small EVM, and it's sort of based off QEMU. It's very similar to small EVM, except it requires full context. But it's a pretty interesting project. lot of other tools are built off Unicorn as well. Okay, that's the talk. I think I'm maybe 3 minutes over, but did anybody have any questions?
So, Caleb, I had a question I just posted earlier. I'll just repeat that. So, is the virtual machine, you mentioned obfuscation techniques before at the start of the presentation. So, you mentioned virtual machine also in that. So, is that related to the mount and unmount permissions many times we see in some Android apps?
Oh, I don't think so. I looked at a couple of malware families that used virtual machines, and basically it was just they had a lot of Java code. They didn't require any additional permissions except maybe internet, and it would download a script that was basically unreadable bytecode that was made for the specific VM in the malware. It didn't really need mount or unmount permissions.
Okay, so it's not actually mounting any kind of new image on a separate partition on the system, right? That's not what we're talking about.
Yeah, that's not what I'm talking about. So imagine you have a function in your code that can do anything. Maybe let's say you implement Python in Java. Let's say you implement Python in your Android application. Then if you're malware, you implement Python in your application. If I look at your application, it just looks like a giant Python engine, and that doesn't do anything bad. But let's say your application downloads some Python scripts from the internet, runs them, and those Python scripts are able to take full advantage of whatever permissions the application had. But instead of Python, it's like a custom language that no one's ever seen before, and it's not human readable, and it's customized for each specific hash, for each specific file. It's been tweaked a little bit. So the only way, there is no easy way to analyze it except to go through opcode by opcode and to understand the virtual machine and all the opcodes in the virtual machine, and it's a lot of work.
And another question I had was so we're talking about Android and Android deobfuscation and the tools that you have. So I'm pretty sure you must be familiar with Tizen. So Android has APK, Tizen has something called TPK, but it's kind of the same thing. It's just like a different wrapper that they have. So is are your tools like something that you can work with the Tizen apps for smart TV applications also? Or
it could be, it may be. It's really just a question of, can you map its code to the ops and the sort of virtual machine structure that Dalvik has.
right.
So do you know if it executes on something like Dalvik, or is it a custom VM that's totally different?
It's kind of similar. It's kind of same. Like Android has SDB, ADB. This one has SDB. Samsung has its own. Like they just changed everything to Samsung. So that's yeah. So I was just wondering. Like, so I'm going to try it out. I'm going to try it out and let you know.
Yeah, I would like to see a TPK, and I would like to see if any tools like DexLib2. If DexLib2 can parse it, then yeah, absolutely, probably work. If they made significant changes to how the virtual machine works, then there might be problems there. Yeah.
Okay. Thanks, Gabriel. Thank you.
I believe Miguel has a question about any semantic analysis tools that work on Android code. I think SmalleyVM is actually doing that, right?
Yes, it is. So you could also probably use something like Dex2Jar and convert the application back to Java, and then use Java semantic analysis tools, which there are many. Soot is one of them. But then you're losing. Decompilation is sometimes messy and results in incorrect code. But I'm not really sure of. I mean, there are other projects actually, I believe, called SmalleyVM, but they're written in other languages and they're not as feature complete. There's one written in Node that I'm aware of that does it. I think because it's more simple, it's probably more robust for what it does, but it doesn't generalize as well as SmalleyVM.
Okay, thank you. Another question. It's a generic question. can you recommend ways to debug an APK? Let's say it's a malware, similar to how Oli debug is used for Windows malware.
Yeah. So Gidra, I haven't used Gidra, but Gidra might work there. That's probably worth checking out. I know the IDA can do Android debugging, and I believe there's also, like I said, they're kind of hard to set up, but there are ways to do IDEA debugging. So like IntelliJ, NetBeans used to have something that you use debugging. I would look for guides online. This is usually what I did. So to be totally honest, I've done that maybe 3 or 4 times, and each time I did it, it took me like 2 full days to figure out how to get it set up and get it working. And I kept running into problems, and the guide was a little bit old, and I kind of got fed up with it. And then the next time I needed to do it, all the tools that I used before were out of date and they didn't work anymore. And yeah, so it's like, oh, this is such a pain. If you did it every day all the time, probably be okay. You'd probably follow a guide, figure it out one time. For me, I just every time I needed to debug an app, I would use small EVM. And if small EVM didn't work, there were bugs. I would fix the bugs until it worked.
Any other questions, guys?
So just one simple question just came to my mind, Caleb. So like for nested app for approaches where there's obfuscation on a nested level, like you have someone who has the encoding first and then some encryption and then further encoding, further encryption, and so on and so forth. So does the application take care of that? Like if there are like multiple rounds of that, and or not? Like, so have you come like I don't know. So I'm just asking.
Yeah, that's a good question. So if during normal execution at runtime, the application would have decrypted the string, then small EVM should be able to do that as well. Because it will, if a function calls another, if a method calls another method, and that method calls itself, and that method calls another method, small EVM should trace through all of that. And if it doesn't, it's because you hit one of those halting problem limits, and you could adjust them, or it could be because there's a bug. Um, those are the two most common cases. The third case is it could be that it's a weird edge case, and Simplify might need a lot of changes to follow it properly, or it might be impossible. Yeah.
Okay. Or in case like many times like if some user interaction is required, like for a legitimate application, like logging in and then some other further action, or for a malware where it's looking for mouse pointer movement across the screen just to identify if it's a real user or not. So is that something that we can bypass in the application and then feed it to simplify or something like that?
Those tend to not be as much of a problem for deobfuscation because in the case of user input, like if you're doing dynamic analysis and you want to extract like what IP addresses does this application communicate with, what URLs, like if you're
Right.
doing like proper antivirus, then you're going to execute as many paths as possible in an emulator and really see what happens. But small EVM doesn't care. It can execute every method in the application. It'll just execute it. And if yeah, and those you probably don't want to do that. You probably want to limit it to just methods contain obfuscated stuff. So if there are some encrypted strings in there, you would execute those. And if those would normally be executed during runtime, then you're dead. Like because of the way obfuscators work, it's very difficult to for attackers to build obfuscators that are so complicated that small EVM won't work. There are a couple little tricks. I've seen people specifically target small EVM to break it. I have seen it before. There are tricks you could use that, there are things that I can't do very easily, but those usually aren't an issue.
So basically, you mean to say that the application is still usable on real life Android apps today, malware and benign applications also, right? We would be able to use them, right? Okay.
Right. But the types of obfuscations it's going to do well against are those that are using reflection, or they're using literal encryption, or they have dead code, white noise. It'll work well against those. But if something's pro-guarded, or it's got all the identifiers have been remapped, that information's gone, and Simplify can't really do a lot there.
Makes sense. Thanks, Caleb. Thank you.
Sure, no problem.
Okay, we have a good comment for you. Very cool talk, and can't wait to try this out.
Well, thanks again for your attention and letting me talk about this. I hope someone gets something out of it. And like I said, if you have any questions after this, feel free to contact me or hop on the Slack with us.
It was a fantastic talk. Thank you.